something, and the ansatz just keeps these rational functions that we have on the right hand side as unknowns. Now observe what happens if you plug in t and j here. We have here a t and j plus 1, so we get r1 q to the n, q to the j plus 1, and also from this term we get an r1 with the original variable. So each of these unknowns occurs with q to the j and with q to the j plus 1. So we have a set of q difference equations. They are coupled, and so we have to first uncouple this system and then solve each equation. And this is a very hard job, especially if things grow so big. So here we have 10 unknowns, which is already relatively big. I also tried, but there was no hope to get anything, and I can even not estimate. So the algorithm is so much complicated. I cannot give an estimate. So probably forever. In this instance, so in other example, it works very fine. It is the means of choice for solving such problems. But this is just too big. So we had to come up with something else. And this is my first attempt that I tried. So we saw the problem was that we have here the variable q to the j in our unknowns, which made this coupled thing of system. So if we want to avoid that, we have to make the q to the j explicit. And for this purpose, I said, okay, let's assume we have here, instead of rational functions, we have just polynomials. And we write these polynomials explicitly as a sum of powers of q to the j. And then our unknown coefficients are just polynomials or rational functions in q and q to the n. The problem is we get, of course, many more unknowns. We might get more terms here in the t and j because we assume that there are no denominators. This forces us to put more terms in until we get a result. But what we gain is that we have, in the end, we have only to solve a linear system. We don't have to do any uncoupling or complicated stuff. We just get a linear system over this rational function field in two indeterminates, and we have to solve the system. So this ansatz turned out fine for the TSPP problem. So it took about 40 days. These things were really big. It took 40 days to conclude it, and under the assumption that the cube case is 100 times more time, estimate is 4,000 days. So still not satisfying. So now the last thing was to, so I said in the previous answers we assumed that there are no denominators. Now we again allow denominators, and we put them here explicitly. So the dk is the denominator of this rational function, and we use a nice thing, a nice property, that these denominators are not completely falling out of the nowhere, but we can have a very good guess of what polynomials can occur in these denominators, because they can be somehow read off from the leading coefficients of the Gröbner basis that we use for proving. But so we look at all the leading coefficients. This gives us a set of candidates that can appear, and then we have to somehow take a multiple of those and try whether we get something. So basically only factors from the leading coefficients can occur here, which already restricts a lot and enables us to get a handle on these denominators. On the next slide I will explain how we then really get them. But we now get candidates by theory. Yeah, and so the nice thing is that, again, so still then we have here the minimal number of terms, which turned out to be 10. And we have smaller coefficients than in the previous ansatz. Everything goes much faster. And we end up with an estimate of 294 days. And I mean, this is already very much in the lifespan of human being, right? So we have now chances to get it. Now, let me explain a little bit more how we solve such systems, because it turns out that if we build up this system, it's so huge that probably even would not fit into the memory. So what can we do there? And there are techniques that are called homomorphic images, or in other words, modular computations. So we have seen we have a linear system over a rational function field in two indeterminates. So what we do, we plug in some integers for these indeterminates. Then all the entries in the matrix become rational numbers. And then, in the second step, we take some prime, a big prime, not 17, but a few million, a prime number, and reduce everything modulo this prime. So then we have a matrix with just integers, entries, and all the calculations are very, very fast, because we don't have a row of coefficients, because everything we compute modulo this prime. So we stay very small, and to see whether this matrix, this system has a solution, is really fast. So this modular arithmetic, you can have a 2000 by 2000 matrix, and it goes just in a second if you compute modulo prime. And so this you can use. If, for example, I mentioned these denominators. We have a bunch of factors that we know they might appear or might not, and we would like to know which ones exactly appear. So we do the ansatz, we omit one of these factors, and we look whether in this modular business we find a solution. And if we don't find a solution in the modular case, we cannot expect to have a solution in the general case. So by this, we can very fast test which factors we need and which one we can leave away. And by these techniques, we can minimize our ansatz, such that we can, in the end, do the whole computation faster. And also for the final computation, what we did is to plug in many values for these indeterminates, and then interpolate the solution. So assume you know the solution is a polynomial of degree 100, then you plug in 101 different values for this indeterminate. You get 101 different solutions, and then you interpolate. And by interpolation, you get a unique polynomial of degree 100. And if you have rational functions as your solution, you do something similar. You can use interpolation, and it's called a reconstruction for rational functions. So from a finite set of points, you can reconstruct the rational function. And this technique allowed to give this precise estimate by the following reasoning. So I found out that I need 1,175 interpolation points for Q, which means that we have rational functions with approximately 600 degree polynomials in the numerator and denominator. And you get this if you fix Q to the n, the other indeterminate, you fix it to some certain value, and then you have to do the computation for Q many times until interpolation gives you some result. And so if you have you go up to 1200, and your interpolation gives you a polynomial of much smaller degree, you can be quite sure that this is the correct one, right? And same thing, I got this estimate for the Q to the n. And then it's a simple calculation. You see that each case takes about a minute. You multiply everything together, and you get 294 days. There were further tricks that reduced the time. In particular, the nice structure of these problems, so these rational functions that come out in the end, they turn out to have lots of very small factors, like q minus 1, q squared minus 1. And the trick is to use the modular solution to recognize these factors and take them out. So I could lower these degrees considerably by guessing these small factors. So as an example, think of you compute with modulus 17, and you find a factor of q plus 16. You guess, okay, this might be a q minus 1. You might be wrong. If you're wrong, then in the next step you will not get a solution, but in this case it was so nice that everything went right. Yeah, so I decrease this number of points, and then